Assalamu alaikum. I'm Hussein Abdu, and in this video I'm going to explain the final and most important results in my final year project entitled Design of a 2 kilobit cache memory array using GC-eDRAM cell implemented in 130 nanometer standard CMOS technology under the supervision of Dr. Nurul Izaila. Here we can see the test bench of the memory array. At the left side of the chip we can see the data inputs which we need to write to the memory. At the other side are the outputs which we read from the memory. At the upper side the write control signals, and at the lower side are the read control signals. Here are the inputs which we will use for the testing operation. The data inputs will be a signal by writing 1, then writing 0, then writing 1. So we will write 1010 to each bit of the memory array. And here we can see that the main voltage source that we are using is 1 volt, and the V reference for the read operation is 0.8 volt, and the boost voltage for the write operation is 1.3 volt. And of course the simulation process was done after doing the parasitic extraction for the chip. Now we can start the simulation. After adjusting the settings, we will start the simulation. Usually the simulation will take up to 5 hours or more, so I will go to the final results directly after the simulation is done. After the simulation is done, we can find here the output signals for the whole process, and the testing was done at the maximum frequency, which is 400 megahertz. We can see here the VDD is 1 volt, the V boost as input 1.3, and the inputs for each decoder, the write decoder, and then for the read decoder. And then after that we can find that the data output after writing and reading is as expected. So we can see here that first we are reading 1, then we are reading 0, then reading 1, then reading 0, and the process goes on. So the output results are as they expected for the simulation. Here we can find the output results for all the signals at each phase and level for the memory array, and we can do the debugging for each operation, whether it's a write operation or read operation for each bit of the cell. I will show now how to do the write operation debugging process. Here we can see the write clock signal and the write enable signal for the write decoder, and the inputs for the write decoder will turn on the last row in the memory array. When this meets the global clock of the memory, this will turn on the pre-WWL driver, and the pre-WWL driver will turn on the WWL driver with the boosted voltage. This will turn on the write word line of the gain cell, as we can see here, and then the operation is done by writing a 1 to the memory, and we can see here that a 1 is written to the storage node of the memory here. For the read operation, the same procedure will take place, where first the read clock signal and the read enable signal will turn on the read decoder, and the output of the read decoder will turn on the read word line driver circuit after meeting the global clock signal. As we can see, the storage node is still contains 1, and the read word line is high. Then the pre-charge circuit will charge the RBL, which is the read bit line, and we can see that because the stored value is 1, so the pre-charge signal will go down and get discharged, and we can see that the sensing amplifier will sense the decrease in the voltage, and within the output will be reading a 1. So the last step, in order to check the memory array is working fine, we can check the storage node of each gain cell or each bit of the memory array from the output signals here. Here we can see that this is a stored 1, then a stored 0, and here we can see that they are not the same GC-eDRAMs. Here we can see that this is GC-eDRAM 1, 2, 3, 4, 5, 6, 7, 8. So the memory is working for the write operation well and for the reading operation also. To measure all the specifications of the memory, different test benches need to be implemented. So for the DRT, for example, a different test bench is implemented. As we can see here, this is the test bench for calculating the DRT, and the data inputs will be all the opposite value of the storage node. So we can make sure that this is the worst case data retention time, and all the clock signals are used as 1 microsecond to make sure that the data retention time is due to the decay, not because of the not complete write operation. And here we can find the simulation results for the data retention time. We can see here the decay at 25 Celsius of the stored one in the memory array or the memory cell, and here we can find that the decay is faster at 85 Celsius, and the DRT is around 70 microseconds at 25 and is around 3 microseconds at 85. That's all for my demonstration, and thank you very much for watching.